Hi everyone and welcome to this new video about three-phase power circuits. This is our example number 5. In this example we will look at a different situation. We have an unbalanced Y-Y system, so we have an unbalanced power circuit. Why is it unbalanced? There are sources here which is connected in the Y configuration. There's also the loads which is also connected in the same Y connection, but the loads are not exactly equal to each other. So if the loads are exactly equal to each other, then we have a balanced system. It must be also true for the sources, which must be in a specific configuration, also specific phase configuration. So in this case, if you look at the values, I will discuss them in more detail shortly. You will see that the ZA, ZB, and ZC are not exactly equal to each other. So we have an unbalanced system. So what is actually different than the former examples? In example number 1 to number 4, we have discussed different three-phase power circuits, and those are all balanced systems. So we have the balanced Y-Y system, Y-delta, delta-Y, and delta-delta systems. Those are all discussed in other videos. You can find them on this channel. And those are, of course, in different configuration, and we can use specific formulas and specific analysis for that. In this situation, because there's an unbalanced system, we cannot assume that this point N is just virtually connected to this point. So we cannot use just this voltages across this load and this voltage across this load and this voltage across this load. So that will be not as easy as we did in the other examples. What do we need to do is we have to apply, so we have to make use of the circuit analysis methods like nodal analysis or the mesh current analysis. So let's look at the example so that will be clear. The following data is given about this Y-Y system and operated at 50 Hz. The phase voltages are VA, VB, VC, and they have all amplitudes of 100 volts. And the phases are 0 degrees, 120 degrees, and minus 120 degrees. So this is the phase orientation and the sequence. The values of the impedance are ZA is just the resistive component R. The ZB is inductive, as you can see, J of XL. And the Z of C is capacitive, minus J of XC. So and the values of those components are shown here. What we like to know is the following. Calculate line currents, IL1, IL2, and IL3. The load voltages, so the voltage drop across each load. The load current, so the current through each load. The total absorbed complex power by the load, so S load, so how much power is absorbed by this load, and how much. The last one, final question, is the total supplied complex power by the sources. So how much power is supplied by these sources, S source and S load. Okay, let's move on first with the calculation of the load, because we don't know much about the load itself. We know only ZA, but we don't know what the values of ZB and ZC in the complex notation. So we only have the formula. So let's first do that, load. And then we can carry out the rest of the calculation. So I will start with the X of L. The reactance of the impedance will be omega times L. We already know this familiar formula. It will be 2 pi times the frequency times 6.35 times 10 to minus 3. That's already given. So what do I have? If I do the math here, you will have very close to ohms. Okay, the next one is the capacitor reactance, 1 over omega times C, which is again a very familiar formula, is 1 over 2 pi times 50 times the capacitor value is 530 micro. And it will be, if you do the math here, it will be very close to 6 ohms. Now I have now the values of the reactances XL and XC. Then I can say the following. Now for ZA, which is just resistor R, it's already given, it's just 4 ohms, so that's actually done. For ZB, which is JX of L, which is J 2 ohms, that's actually also done. And for the Z of C, for the impedance, is minus JX of C, which is minus J 6 ohms. So I have now all of the all three loads, 4 ohms, J2 ohms, and minus J6 ohms. And I will use these in the analysis. The next analysis will be determining the line voltage, line currents, IL1, IL2, and IL3. Because it is an unbalanced system, I have to apply use the circuit analysis methods like mesh current analysis, what I said already in the beginning of the video. So I will make a loop for the top one. I will also use this loop at the bottom, so I have two loops, and I will make two mesh currents. So I will have, if I draw the mesh for this one, that will be I1, and for this one I will have a I2. So I will have to set up these equations for the mesh analysis. So this will be the next step. So let's first do equation 1. I can start at any point I want, and I have to again come back to the same point. So if I start at point A, I will have VB minus VC, and then the summation of the ZB and ZC times this current I1, because it is our orientation, but minus because it is in the opposite direction, minus the ZB times I2. So what we have is the following. So Z of VB, I mean minus VC, plus ZB plus Z of C times I1 minus Z of B times I2, which will result in 0. That's the loop voltage for this first one. For the second one, I will start at point A, and I will move again, and I will end up point A. Again, VA minus VB, and the summation of these two impedances times I2, because that's our orientation, and then minus ZB times I1, because it's in this case the opposite current. So what we have is the VA minus the VB plus ZA plus ZB times I2 minus ZB times I1, which is 0. And what I want to do now is I will simplify, or I will write it down in a different form. This expression I will keep it, these terms I will keep it at the left side, and I will have the voltages at the right side. I will do the same for the second term. So I have the following. If I move all the voltages to the right side, and I keep the currents and the impedance at the left side, so I have got the following expression: ZB plus ZC times I1 minus ZB times I2, which is V of C minus V of B. And the other one, I will again go in the direction on the sequence I1 and I2, so I will have to first write this one. It will be handy in the further calculation. So I will have the minus ZB times I1 plus Z of A plus Z of B, all of them times I2, which will be VB minus VA. Alright, so let's now substitute the given values in all those expressions. So I will move to the right. So what do I have? I have the value of ZB and ZC and ZA. All of them are given here. I can also use the values for the VC and VA and VB, of course, in the polar expression. And I can continue with the analysis. So what I have is the following. This is the J, let me write down, J2 minus J6 times I1 minus J2 times I2. Now VC is given as 100 volts, phase of minus 120 degrees, and then minus 100 volts again, but this time plus 120 degrees for the VB. Now if I continue for the second equation, it will be minus ZB is minus J2 times I1 plus will be 4 plus J2 times I2 will be 100 volts phase 120 degrees minus 100 volts phase 0 degrees. All right. Now I can simplify this. I can simplify this term, and also these expressions which are given in the polar expression, I will transform these into the rectangular expression, and again add them up and simplify them such that I have only in rectangular expression. So I will need to do that, but that will be also the usual formula we have discussed in the video about complex numbers and phasors. So I will leave the details out. I will just give you the results. So what do I have is the following: minus J4 for the first one times I1 minus J2 times I2 is equal to, and if you do the math here, what I just said, for converting from the polar expression to the rectangular expression, you will have minus J 100 times square root of 3. That's actually for the first equation. For this one, I will just copy this and again convert this to the rectangular expression. So what I have is the following: minus J 2I1 plus 4 plus J2. I2 will be, if you convert that to the right side also in the rectangular expression, you will have minus 150 plus J 50 times square root of 3. Okay, now I will now use these equations and carry out the analysis to calculate I1 and I2. From that I can calculate the line currents and of course the other unknowns in this analysis. What I first would like to do is I can simplify actually equation number 1, because I have minus J, and minus J in all of the equations. This is a 2, so I can divide by minus J and I have a simplified expression. So I can use the following. I can say this is 4 times I1 plus 2 times I2, which will be 100 times square root of 3. That's actually for the first equation. And this one will stay as it is. So I will use this one and this one, and I will need to use them later on for our further analysis. So let's move on. What I would like to do now is I will place these equations. I will a little bit zoom out. So I will have to take this. This is not necessary anymore. So I will get rid of this one. So I will have to take this first one and also this one. And I will have to transform these two equations in matrix form. So what I would like to do is the following: matrix form. So this will be converted in the following situation. I will have A, some matrix, times the current vector I, which is equal to the result B vector. So I will have to set this matrix A and the current vector I and the solution vector B. So I mean B is the values after the equation at the right side. So what I would like to do using this formula, using this analysis, is I would like to calculate the vector I, which is of course I1 and I2. I can use of course the inverse of the matrix A, and I have to directly the values for I1 and I2. So let's fill in the values for, so I have the 4 here and a 2 there, so 4 here and 2 here. So I will have the following: 4 and 2, and this will be minus J2, and this will be 4 plus J2. This will be A1, this will be A2, that's for actually vector I. This will be 100 square root of 3. This will be minus 150 plus J 50 square root of 3. Maybe I will make this a little bit larger so you have better. Okay. Alright, so this is actually the expression for the A. So this is actually A. This is the matrix A. This is the current vector I, and this is the vector B. So I would like to determine what I would like to do, because if you look at this expression, I would like to determine the inverse of the matrix A. So first, let's do that. So what is the inverse of the matrix A? How do we calculate the inverse of the matrix? So inverse of this matrix A, inverse of the matrix A which will be 1 over the determinant of this matrix, times, what you do is actually the following. Determinant of the matrix, I will do that shortly, but for this this section, this part, I will swap this and this term. So I will have a 4 here and 4 plus j2 there, and this will have an opposite sign. So I will have the following. So I will have 4 plus j2, and this will be 4, this will be minus 2, and this will be plus j2. And the determinant of A will be, looking at this of course, will be 4 times this minus 2 times minus j2. So it will be 4 times 4 plus j2 minus 2 times minus j2. That's actually for the for this, and if you do the math here, you will have 16 plus j12. This is actually for the depth of A. Okay, now if I now substitute everything here, I will have the following: 1 over 16 plus j of 12, and then 4 plus j2 minus 2 j2, and then 4, and this is actually the matrix we would like to determine. If you have calculated this one and determined the expression for this one, you can multiply this with a b because this is the b. So actually what I do now following is I will use this, multiply by this factor, and I will have the I. So let's move on. So I will have the I, which is A inverse times B. What is A inverse? We already calculated this. This is 1 over 16 plus j12. This is 4 plus j2 minus 2 j2 and a 4. And you will have this factor, that is 100 square root of 3 minus 150 plus j 50 times I will write down more clearly. So j 50 times square root of 3, and this is actually the expression. Now if you work this also out, just doing the matrix multiplication and with the factors, you will have the following answer for I. So I is equal to 50.4 phase minus 27 degrees, and the other one will be 45.9 phase 94 degrees, and this is of course in amperes. So this is actually the vector what I required for A1 and A2, and this will give us of course A1, which is already given in the phasor notation, 50.4 phase 27 degrees in amperes, and A2 will be 45.9 phase 94 degrees. These are the two mesh currents actually what we required to calculate. Again, what you need to do from here to there, you need to calculate the matrix, this one inverse of this matrix times this vector. It will give you another vector here, and you will have to calculate also the multiplication with this factor here with this new factor, and you will have the following expression after you convert the rectangular expression to the polar expression. So you will have to do a couple of steps in between, but it is just straightforward, so I will leave the details also out. So I have these two currents. So what I now like to do is I would like to use these two, I1 and I2, to determine line current, because those were the questions. So line current, IL1, IL2, and IL3. If I now look carefully, IL1 is minus I2. This is actually what's shown here. If I look at IL2, which is actually I2 minus I1. So it is in the direction of I2, but it is in the opposite direction of I1. If I want to know IL3, it's actually the same direction as I1. So if I now move to the next part, which are the line currents. So let's move on with the line currents. That's the next one. So what do I have is the following. I have IL1, which is the minus I2, which is already calculated, and which is minus 45.9 phase 94 degrees in amperes. And you can of course use this minus sign because it is 180 degrees out of phase. So you can add here minus 180 and you will have a positive sign for the amplitude. So you will have 45.9 phase of minus 86 degrees. There's exactly the same expression. If you now do the math also for IL2, which is I2 minus I1, which is 45.9 phase 94 minus 50.4 phase minus 27, which is again calculated here. Look at the right side. We have calculated here, so this is I1, so I2. I've substituted all of them here. So let me zoom out a little bit more. So this is one I1, I2, I minus I2, so this one, and IL2 is this one. So I just substitute the values. And if I now do the math here, again converting from the polar notation to rectangular notation, again add them up and again back to the polar expression. I will leave the details again out. I've done this in more detail in other videos, so that will be helpful to look at the videos for the example number 1 to number 4, also to the complex numbers and the phasors video. So I will have the following is 83.9 in a phase of 127, of course also in amperes. So the IL3, the last one, which is exactly equal to I1, and this is exactly 50.4 phase minus 27 degrees. So I have actually all of the line currents. And that's actually for the line currents. So I move to the next part. Let's look at the question. So the following question is, what are the load currents? Now, since we know the IL1, then the IZ of A will be exactly the same because it is in series. Same can be said for the IL2 because it is exactly the same as IZ of B because it's in series, and for IL3 is exactly the same as IZ of C. So this one for question C is very simple, so I can actually write it down very easily. So this one was question B, so I will now move to question C. I will do that here. So question C were the load currents, and I can say the IZ of A, let me do that in black. So IZ of A, which is IL1, IZ of B, which is IL2, and IZ of C, which is IL3. And we have all determined that, so it's actually shown here, all of them. Okay, so let's move on with the following problem. The following problem is about power, so that's actually very interesting. We have to look at the total absorbed complex power, and we have to also look at the total supplied complex power. Because we are dealing with complex powers, so the apparent power, etc., we have to use the RMS values of the currents and the voltages. Because these are all given in amplitudes, we have to actually use the square root of 2 divided by the square root of 2, but we have never done that in the analysis here. So what I would need to use is the RMS value of the voltage and also the RMS values of the associated current. So we have to remember that, otherwise we have a factor of 2, because square root of 2 times square root of 2 for the current and the voltage. We have square root of 2 there, we have to remember. So let's move on to the powers. So let's move on to question D. So total complex power absorbed by the loads. Now, if you now look at the loads, we have 3 loads. So what you can see is say the following. You can say if I now have the S of load, which will be a summation of S of ZA due to the impedance ZA, S of ZB, and S of ZC. So if I now know each of them, and I just add them up, just summation in linear form, I will have the answer. But I know the complex power in general form is equal to the RMS value times the current RMS value and the complex conjugate of that. Because I don't have the RMS value, I have not used them, I can also use the following formula. I can also say it is also equal to a half times the peak value of the voltage times the peak value of the current, of course, again in the complex conjugate form. So you might use the RMS values of the voltage and the current in the complex conjugate form, or you can use this, and we have, of course, calculated in the peak form, so this one will be handy in our case. So I will use this for each of these expressions. So let's move on. So let's do that for impedance Z of A. What do I have? I have, of course, the SZ of A, which is 0.5 times the voltage of ZA times its current. That's actually what I need to know in complex conjugate form. But do I know the VZ of A? So that's actually the load voltages. So I need the load voltages. That's also true for this one and also for this one. So what are the load voltages? First, let's calculate that. So VZ of A is equal to IZ of A times the Z of A. And I already know IZ of A because it is just the IL1, because this one. So if I now substitute the values for that, I will have 45.9 phase minus 68 degrees times the value of ZA, which is just a resistor, so it is just pure ohmic, 4 ohms and 0 phase orientation. I will have an expression for the voltage, which is 183.6 with a phase of minus 68 degrees, and it's in volts. So if I now use the value of the IZ of A in a complex conjugate form, then this will be, of course, a plus sign. And I will use this because I already calculated this. Then I have the following. SZ of A will be a half times 183.6 phase minus 86 degrees and the complex conjugate of the current. So I will have 45.9 and then plus 68 degrees. And I will have the following expression for the apparent power. If you look carefully, this phase will and this phase will of course cancel each other out, and we have 0 degrees phase shift for this apparent power. That's of course understandable because we have a real component here, so it's a pure ohmic system, and you will do half times 183.6 times 45.9. That will be the amplitude here. So I will have the following: 4,214 and a phase orientation of 0 degrees, and I will just denote this by VA, but it's just also watts. Now in a similar form I will do that for ZB and also for ZC, so let's move on. So for ZB, what do I have? I will have ZB, S of that is equal to half times the voltage of the ZB times the current of that complex conjugate. Still, I don't know the voltage across the load, so I will have to calculate this. So that will be I of ZB times ZB, which is also determined here. So IZB is equal to IL2, and IL2 is shown here. So if I now substitute this value here and also the Z of B, which is inductive, which was J2. So if I now, and if I convert that to the polar notation, so I will just write down here. So I will have this. This was the given value, and this will of course be in the polar notation, this one. So I will use that. So what I have the following: 83.9 phase 125. That's actually for the current, yeah, and times the 2 phase 90 degrees. Now if you now do the math here, you will have 167.8 phase 215 degrees in volts. Okay, so this was apparent power for ZA. Now we are very close to the apparent power of ZB. So what we have is ZB, and the apparent power of that will be a half times this one, 167.8 phase of 250 degrees, 15 degrees, and times the complex conjugate of the current, which will be 83.9, and phase of minus 125. And if you do the math here, you will have 7039 phase of 90 degrees. As you can see, it's just pure inductive because it is plus 90 degrees. So if you do the same procedure for ZC, so again, I will just write down what the formula is for the S of ZC, which is half times the voltage of that times its associated current, but then the complex conjugate of that will be, of course, we have, of course, the Z of C, which is minus J6, which is 6 phase minus 90 degrees in polar representation, because we need that. So what we have is the following for V Z of C, which will be I Z of C times the Z of C. And I know I Z of C, which is shown here, because I Z of C is IL3, and IL3 is this one. So I can move on with 15.4 phase minus 27. So 50.4 minus 27 degrees, and then using 6 minus 90 degrees. And if you do the math here, you will have the voltage for the impedance Z of C, so the voltage across the impedance Z of C. What would you have is the following: you will have 302.4 minus 170 degrees, 117 degrees. Okay, now we have actually almost the S Z of C also, which is a half times 302.4 phase minus 117, and the complex conjugate of the current, this one, will be plus 27, so it will be 50.4 plus 27 degrees. If you again do the math here correctly, you will have 7620 phase minus 90 degrees, again in volt amperes. Now, what you recognize is the pure ohmic system load will give a zero phase shift, pure inductive will give a plus 90 degrees, and pure capacitive system will give us minus 90 degrees phase shift for the apparent powers. So then, what do I have for the total system? I will have the S load will be, of course, the summation of these one. So that will be this one. I will a little bit zoom out. This one, 44,214 phase 0 degrees plus 7,039 90 degrees, and then plus 7,620 phase 90 degrees. And if you do again the math here by converting the polar representation to the rectangle, but this time it is very simple because this is pure imaginary in the positive y direction, this is pure imaginary in the positive minus y direction. This is pure resistive. So actually this one is very straightforward. It will be 4214 plus J 7039 minus J 7620. And if you simplify this, you will have 4240 minus, because these two imaginary values will give you effective imaginary part, will be 581, and it will be of course in volts amperes. And if you convert this to the polar representation, again using the standard formulas for determining the length and the phase, then we will have 4254, and the phase will be approximately 8 degrees. And it is also in volt amperes. So what you can see is we have a phase of -8 degrees. That will mean actually we have a leading power factor for the load. So if I want to know the power factor, which is actually not a question, but it will be interesting. So the power factor will be the cosine of this angle, and it is leading because we have a minus. If this is a plus, it will be a lagging. So that will be, if you calculate this, it will be 0.99 leading. It's almost 1, so it's actually not that bad. Okay, we are done actually for the load. So if you do the math again for the same procedure for the sources, what do I have to do for the source? I will have to look, if you look at the diagram, the circuit, what I want to do is the following. I will need to calculate total supplied power, complex power, by the voltage sources. So I will do the following. I would like to know what is the voltage VA times its current. Of course, again, the complex conjugate, then I will divide by 2 because I use the amplitudes here. I will do similar for the VA and VB. I will do the same for VC, and I will add them up. So actually, that is the whole business for the sources. So that will be exactly the same procedure. So I will do that also for question A, all the way down, all the way down. So I will have also the last one will be, so total complex power supplied by the sources. That's the last one. So we will call this S source, will be S due to V of A plus S due to V of B plus S due to V of C. Now, what is S of V of A? Which is half times, because we use the amplitudes and not the RMS values, it will be V of A times its phase current, or the current which is supplied by the V of A. Of course, the complex conjugate of that. And if you do the math again for the other one, so V of B and V of C, what you have is exactly the same procedure. So it will be V of B times the phase current of B, complex conjugate of that, and V of C times the phase current of C and the complex conjugate of that. So if I now use the values from the V of A, V of B, V of C, and also the phase currents. What are the phase currents actually here? The phase currents, because if you look at the circuit again, so let me move up. I will have this. This current, which is supplied by the voltage source VA, will be exactly equal to IL1. That's actually what this, and that's for the IL2, that's for IL3. So I can already know phase currents are IL1, IL2, IL3 for the voltage sources VA, VB, and VC, respectively. So I can move on with the calculations using the line currents. So I can say the following, in this case, of course. So I can say the half times the VA times IL1 complex conjugate. This will be half times the VB times IL2, again the complex conjugate of that. And I have the half times the VC times the IL3 and the complex conjugate of that. Now if you substitute the values here, what do you have? You will have a half, of course, that is standard, times the VA, which is 100 phase 0 degrees, that's what was given. And we have calculated IL1, which was 45 5.9. But if you now take the complex conjugate, you will have plus 68. And if you do the math here correctly, you will have 2295 phase 68 degrees in volt amperes. That's actually for the first one. Okay, the second one, half times 100 phase 120 degrees. Now we have to take the IL2. Again, the complex conjugate of that will be 83.9. Phase will be minus 127. And if you do the math here also correctly, you will have 2520 phase of minus 90, minus 5 degrees. Excuse me. I will erase this because this is the correct one. This is 4195 phase of minus 5 degrees. That's actually for the second one. And for the last one will be half times 100 volts with the phase orientation of minus 120 degrees. And the phase of the current of IL3, again in complex conjugate form, will be 50.4 phase 27. It was minus 27, it is now plus 27 due to the complex conjugate. And you will have 2000, that was actually for this one, 2520 phase minus 93 degrees, and it will be also volt amperes. So I have actually all of them, and I can now add the values here. So I will have the following. This will be 2295 phase 86 degrees plus 4195 phase of minus 5 degrees, and this will be 2520 phase of minus 93 degrees. And if you do the math here for the source, what you need to do is the following. You will have to convert this again in the rectangular form, all of them, and add the real parts and the imaginary parts, and again convert to the polar notation. You will have the following in the rectangular form: 4207 minus J 593 in volt amperes. And if you convert this to the polar expression, you will have 4249, and it will be phase minus 8 degrees in volt amperes. So if I now underscore this in red, what you recognize here is the following. The source has a value of 4249 phase minus 8 degrees, and I will have 4254 also the same phase. So this is actually not surprising, because what you deliver must be also, what you supply must be also absorbed by the loads, if you of course consider a complete ideal system, which is considered in this example. The small error here, what we have in the amplitude, is due to the rounding off, of course, because I've made the calculations a little bit easy by not using commas, so I have used just the whole numbers. That's actually the small differences due to that. So in total, what we have is the following. In effect, in total, we have, or we see, S source, so I will write it down in blue. The S source will be equal to, or must be also equal to, S load. That's very interesting. So that's also very important. So you can actually make a check if you have, of course, no losses elsewhere in the transmission line or whatever. Now you will need to have the source apparent power equal to the load apparent power. That's actually for this lengthy, for this example. I hope it is clear, because it is a balanced system. It is, of course, a lot of work setting up the equation. I have also skipped some of the steps, otherwise it will be too lengthy video. But go through the steps, and if you have questions or comments, please place it in the comment section. I will try to answer them as soon as possible. And also look at the other examples, example number 1 to example number 4. I will give you a lot of background, and also how we did it in the balanced system, because that will also helpful when you want to start analyzing the unbalanced system, because it is a little bit complicated and challenging. Alright, see you next time, and don't forget to share and like, and don't forget to subscribe, and take care.